Quantum computing is no longer science fiction, it's science fact. And it's about to transform everything, from cybersecurity and drug discovery to climate modeling, and even how we understand reality itself. While classical computers rely on binary bits, zeros and ones to process information, quantum computers use qubits, which can exist in multiple states at once. That allows quantum machines to solve complex problems in seconds. Problems that would take classical computers millions of years. In 2025, this isn't just a theoretical concept. It's real, and it's already happening. So what makes quantum computing different from classical computing? How does it actually work? What will it be capable of by 2035? And what breakthroughs are already happening right now? To understand quantum computing, we first need to understand what sets it apart from the classical machines we use every day. Classical computers operate on bits, binary digits that can either be 0 or 1. All modern software, from your smartphone to the most advanced supercomputer, is built on combinations of these two values. Quantum computers use qubits, and unlike bits, qubits can exist in a state called superposition where they array both 0 and 1 at the same time. Imagine flipping a coin. While it's spinning, it's not just heads or tails, it's both. That's superposition. But qubits can also be entangled. This means the state of one qubit instantly affects the state of another, even if they're far apart. Entanglement creates powerful correlations that classical systems simply can't replicate. Combine superposition and entanglement, and you get exponential power. 2 qubits represent for states at once. 10 represent over 1,000, and 50 can represent more states than atoms in the universe. Quantum gates also behave differently. In classical computing, you have logic gates like an OR and NOT, which follow fixed rules. In quantum computing, gates are reversible and operate on probability amplitudes, not fixed values. Gates like the Hadamard, PolyX, and CNOT manipulate qubits in ways that let quantum algorithms explore countless potential solutions simultaneously. When the system is measured, it collapses into one of those possibilities, the correct one, if the algorithm worked as intended. That's why, in 2019, Google's 53-qubit quantum computer, Sycamore, achieved quantum supremacy by solving a problem in 200 seconds. That would take the fastest supercomputer over 10,000 years. Looking ahead to the next decade, quantum computing could revolutionize nearly every major field. In medicine, quantum simulations will allow researchers to model molecules, proteins, and drug interactions at atomic precision, something classical computers struggle with. This could cut drug development time from years to months and help us fight diseases like cancer, Alzheimer's, and antibiotic resistance. In climate science, quantum models will simulate Earth's complex weather and atmospheric systems with far greater accuracy, improving everything from hurricane prediction to sustainable farming to energy grid management. In cybersecurity, quantum computers could eventually break RSA encryption, something that would render current internet security obsolete. But quantum cryptography offers new defenses too, like quantum key distribution (QKD), which is already being tested in secure communication networks around the world. In finance and logistics, quantum algorithms will optimize portfolio strategies, risk assessment, and even supply chain routes for global shipping, aviation, and traffic management in real time. In AI, quantum machine learning may reduce model training times from weeks to minutes and create neural networks that learn patterns far faster and with less data. And in national defense, countries like the US, China, and the EU are investing billions into quantum radar, secure battlefield communications, and space-based quantum sensors. But this isn't just what's coming. It's already starting. In 2025, IBM's Quantum System 1 is accessible via the cloud, offering 127-qubit systems for developers and researchers. Google is working on error correction to improve the reliability of Sycamore. Microsoft is building toward topological qubits, which are more stable. Startups like Rigetti, Ion, and Xanadu are developing scalable platforms based on trap ions, superconducting circuits, and photonics. Amazon and Microsoft now offer quantum access through cloud services like Breakit and Azure Quantum. You can literally code a quantum program in Python and run it on a real quantum machine today. Industries are already experimenting. Volkswagen is using quantum models to optimize traffic in German cities. Morgan Chase is working on quantum finance tools. BASF and Roche are exploring quantum chemistry simulations. And universities around the world are launching degree programs to train a new generation of quantum engineers and developers. Of course, quantum computing still faces serious challenges. Qubits are incredibly delicate. Even the tiniest disturbance, vibration, heat, or electromagnetic noise can cause decoherence and ruin a computation. That's why quantum machines must be cooled to near absolute zero in cryogenic environments. We also need effective quantum error correction, which often requires hundreds or even thousands of physical qubits to create a single reliable logical qubit. Building large-scale quantum processors will require huge breakthroughs in materials science, chip design, and scalable architectures. Software is another frontier. Quantum algorithms are vastly different from classical ones, and most of today's programmers don't yet have the tools or training to work with quantum systems effectively. New programming languages, better compilers, and smarter quantum classical hybrid platforms are being developed, but we're still in the early days. And education is critical. The world needs thousands of trained quantum scientists, engineers, and developers. That's why universities, startups, and tech giants are investing heavily in open access learning platforms, simulators, and hands-on quantum programming environments like Qiskit and CERT. Even with all these hurdles, the progress is accelerating. The transistor revolutionized classical computing in the 1950s. We're now in the vacuum tube era of quantum computing, but the transistor moment, it's coming faster than anyone expected. So what's the verdict? Classical computing built the digital world we live in today, but quantum computing will build the world of tomorrow. Over the next decade, it could transform industries, redefine what machines are capable of, and unlock new dimensions of problem solving. By 2035, we could be living in a world powered by quantum design medicines, quantum secure communication, and AI that thinks orders of magnitude faster than anything we know. And in 2025, that future is already beginning to take shape. If this video opened your mind to what's coming, subscribe now to feed the mind and turn on notifications. Every week, we explore the technologies shaping the next 50 years of humanity. And if you want to understand how quantum will collide with AI in the near future, check out our next video. Until then, stay curious and keep feeding your mind.